Hello everybody and welcome back. Today we're going to be showing how to do differential equations to solve problems involving pendulums. So let's return to this example where we have a pendulum of length L and mass M. And so let's take a look at the torque. The torque on this mass object down here. And so the formula for torque is R, the length of its axis that's acting about the torque, times the force, times sine of theta. And so essentially what we can do is we can substitute, okay, well the length of its axis is actually L because it's moving about this point here. So we can say that torque equals L. The force is, we're going to say it's negative mg because let's say that the direction towards the axis is positive and away from the axis is negative. So times negative mg times sine of theta. And so also we know that torque equals I, its rotational inertia, moment of inertia, times alpha, which is its angular acceleration. And so for this case, for a point mass, we're just going to assume that all the mass is concentrated in one area. Then we can say that mr squared equals to I. And so what we can do is we can kind of combine these equations. We can say that, okay, so if I alpha equals RF sine theta, then we can substitute these different values in. So what we can say, R in this case is again going to be L. So we have mL squared, and then times this acceleration, and that acceleration equals the second derivative of the angle with respect to time, and it also equals the first derivative of the angular velocity with respect to time. And so anyway, so we have mL squared times the second derivative of theta with respect to time, and that's going to equal negative LmG sine theta. And so immediately what we can see is that we can cancel the m's there, and then we can divide, or well, we can also cancel these l's here, and then we can divide by L on both sides. And so what we end up with, if we simplify it, is the second derivative of the angle with respect to time equals negative G over L sine theta. And so what we can do is we can rearrange this to get it more simple. So you can say a second derivative of theta, and we're all getting it onto one side, so plus G over L sine theta equals 0. And so for very small values of sine, what we can say is that sine of theta equals theta for small angles. And the reason why this is true is because the approximation for sine closely resembles a very linear approximation for theta. And there's a whole video that I have talking about that, so if you want to go see it, it's on my channel. And so if we simplify this, what we have is that the second derivative plus G over L theta equals 0. Now this is a much simpler differential equation to solve. And the way that we can go about solving this is by assuming that theta takes the form of e to the RT. And the reason why we can do this is because then when we substitute it in, we can get values for R, and then we can plug that back in and get a differential equation solution. So we can say that d theta dt equals the derivative of this, so that is r e to the RT. And we can also say that the second derivative of theta with respect to time equals r squared e to the RT. So when we plug this back into our equation, what we have is r squared e to the RT plus g over L e to the RT equals 0. And so we can factor out an e to the RT term. And so for this to equal 0, it never can equal 0, because if we look at the graph, I mean, it's pretty close right there, and then it sort of accelerates, but right here, it's never going to actually equal 0. So this term can never equal 0. So that means that this has to equal 0. So r squared plus g over L must equal 0. And so what we can do is we can subtract g over L on both sides. So we say r squared equals negative g over L, take the square root of both sides, and we're going to get an imaginary result. And so what we get is that r equals plus or minus I, and then times the square root of g over L. And so when we do that, the solution to this usually takes the form of, so in this case it would be e to the I something, but e to the I whatever is just the sum of cosine and sine. And there's a whole video, again, where I talk about the approximation for sine and how for small angles, sine of theta equals theta. That same video also talks about how this sort of idea of e to the I something and how that is just a sum of cosine and sine. So what it really equals, if we plug back in this r, is that theta equals some constant times the cosine of the square root of g over L, that's a bigger square root, times time, plus C2 sine of the square root of g over L times time. So now if we take a look at what the solution to this pendulum differential equation looks like, we can see, okay, so I've plugged in different values. So we have the value for the acceleration due to gravity, 9.8 meters per second squared. And then we have 2, which in the original example problem in the algebra video on pendulums was the length of the pendulum, 2 meters. And so what we can see is that the graph looks like this. It's this oscillatory motion of this pendulum. And depending on these different constants, it can sort of move around. So you could, for example, make it have a really high amplitude. You could make it kind of stretch like this and move around and do all sorts of different things. But the main thing is just really to show that it's oscillatory motion. That's the important takeaway from this.